This is lesson 2.2, properties of matrix operations. In our last lesson, we looked at how to add matrices, multiply by a scalar, and multiply two matrices together. And in this lesson, we're going to do more of those operations. But we're going to start by just looking at some of the properties that exist related to those operations. A lot of things that actually mirror things that we can do and what we know about mathematical operations with real numbers. So for example, I decided to just type this all up into the notes instead of writing it all as we go through. All of this is in the textbook, so you can find it there, or if you want, you can print this, or just know that this is here in the video. But these are all of the different properties that relate to those different operations that we talked about from lesson 1. And so what we have, for example, is if A, B, and C are m by n matrices, and C and D are scalars. Again, assuming that the matrices are of a size that would allow us to do these operations. The idea that adding two matrices together is associative, that I can, commutative, that I can say A plus B is equal to B plus A. The order that I add those two together doesn't matter. Makes sense because if I'm just adding corresponding entries anyway, it doesn't matter what order I write those matrices or add those matrices in. Similarly, if I'm adding three matrices, the order that I add them does not matter. And so on. So I'm not gonna go through each one of these in detail again, but these mirror a lot of the properties or many of the properties that we have with real numbers. Maybe just a couple that I want to just highlight. If you look down at 5 and 6, for example, if we're adding matrices and then multiplying by a scalar, you can multiply each matrix by the scalar first, or add them and then multiply by the scalar. In number 7, 8, and 9, we do introduce this idea of what's called a zero matrix. And a zero matrix is exactly that. It's a matrix where all of the entries are zero. So it kind of makes sense then if I take a matrix and add a bunch of zeros to it, I'm just going to get that same matrix back in number 7. Number 8, if I add a matrix and its exact opposite, where all the entries are the exact opposite values, I'm going to get a zero matrix back. And so on. So again, just be aware that these exist. I'm not expecting to memorize these or anything, but just know that these are here. So what we're going to do is just maybe do a few examples that apply some of these, and just almost through at least one example, kind of verify it for that example to see that, oh yeah, that really does work. So we've got three matrices here. We've got A, B, and C. And again, we're just going to work with 2 by 2 to kind of keep this a little simple. And so, for example, in the first one, we're going to multiply A times B, and then multiply by C, and then we're going to flip the order around, and we're going to multiply B and C first, and then A, just to again, verify that we do get the same matrix back. And then we've got a last little part here, is A times B the same as B times A? Again, if you want to do these on your own first, that's great. Otherwise, you can just kind of keep rolling here, and we'll go through this together. So for the first one, we're going to multiply A times B, and I'm just going to kind of do this, I think, just kind of in my head here. So A times B is going to be 5 and 9 is 14, and then we've got -1 and 0 is -1, and then for our second row, we've got 10 and -12 is -2, and then -2 and 0 is -2. So this is AB, and now we are going to multiply this by C. And so that is going to give us a final matrix of, 28 and -4 is 24. -28 and -1 is -29. -4 and -8 is -12. And then +4 and -2 is a +2. So that is our final result, having taken A times B and then times C. So now let's do the same thing, but let's change up the order here. So we're going to take B times C first. So in this case, taking B times C, we have 10 and -4 is 6. -10 and -1 is -11. And then for the second row, 6 and 0 is 6. And -6 and 0 is -6. So this is B times C. And now we're going to multiply that by A. Obviously, order that we write these is important. So if it says A times, we want to make sure that the A matrix is sitting in front of the BC matrix. So that's 1, 3, 2, and -4. And so if we did this right, if I did this right, we should get the same matrix that we just did in the previous example. So we've got 6 and 18 is 24. That's a good start. -11 and -18 is -29. And then for the second row, 12 and -24 is -12. And -22 and 24 is a +2. So we can see that these two things are the same, that it didn't matter if we took A times B first and then times C, or took B times C and then multiplied it by A, as long as we kept those matrices in order. So for the next part of this, is A times B equal to B times A? Well, we already have, up in the previous example, we have A times B here. So we really just need to find BA and just see, do we get the same thing? So if I take B times A, and I think we're going to rewrite these so I don't have to kind of, in my head, remember which row, which column. So B and then A, 1, 3, 2, -4. So here, first row, the first entry, is going to be 5 and -2 is 3. And I can actually just stop here, right? Because I got 14 when I took A times B. I get 3 when I take B times A. Clearly, these matrices are not going to be the same. Really just firming the point that multiplication with matrices is associative, but it's not commutative. In other words, we can do multiplication in keeping the matrices in order. It doesn't matter which ones we multiply first, but we can't switch the order of those matrices. All right, so let's talk about the identity matrix next. Identity matrix is really just like 1 is the identity in the real number system. The identity matrix is a matrix where basically what you have is a diagonal of all 1s, and then everything else is 0. This is the identity matrix. And we often will call this just I for the identity matrix, okay? And again, with the identity matrix, there's a number of things that we can show and do with this. And so let's take a look at some of that. So here we've got a 2x3 matrix. We're calling this matrix A, and we're going to just multiply this by the identity matrix. Now, the identity matrix is always a square matrix. So this is always going to be n by n. So when I multiply a 2x3 matrix, depending on what order I multiply by, that's going to change the size of my identity matrix. So for example, if I'm going to take A times I, so this is 3, -1, 4, 2, 1, -2. So again, this is a 2x3 matrix. Remember in the last lesson, we talked about the fact that whatever I multiply by, the rows, or excuse me, the columns in the first matrix have to be the same as the rows in the second matrix. So if I have 3 columns here, I have to have 3 rows in my second matrix. So this is going to be a 3x3 identity matrix that we're going to be multiplying by. So when I multiply these together, this is a 3x3, I will get a 2x3 matrix. Remember, the first and last give me the size. So I'll have a 2x3 when I am done with this. So just going through this, and you can probably kind of see what's going to happen here. When I do the first row times the first column, I'm going to multiply 3 times 1. Everything else is going to be 0. I'm just going to get 3. When I take the first row times the second column, the 3 is multiplied by 0, the 4 is multiplied by 0. Only the -1 gets multiplied by 1. That's going to be a -1. And then for the last column, 3 times 0, -1 times 0, 4 times 1 just gives me the 4. Same idea is going to happen in the second row, and what I end up with is the exact same matrix that I started with. So the question is, does it work the other way? Can I multiply by the identity matrix first and then the matrix A? So in this case, now if I'm going to do the identity first, it needs to be a 2x2 multiplied by A. And so here, because I'm taking a 2 by 2 times a 2 by 3, I'll get a 2 by 3 in my final answer. And so I've got, again, 1, 0 times 3, 2 is 3. 1, 0 times negative 1, 1 is negative 1. And then 4. And in the bottom, we get 0. Basically, if you think about this, we're taking this row times each of the columns. Well, in essence, because this 0 is going to be attached to the first row and the 1 is attached to the second row, we're basically multiplying that first row by zeros every time. We're taking the second row times 1. We're just going to get that second row back. So mathematically, that's why this is working, that when you multiply by the identity, whether you multiply by the identity on the left-hand side or the right-hand side, doesn't matter. You will always get your original back. So in other words, a times I is the same as I times A is the same as just getting A. And that'll always be true for any identity matrix and multiplication. A couple other things then that kind of relate to this. In the real number system, if I took 7 to the 0, that's just going to be 1. Anything to the 0 power is 1 in the real number system. 1, again, being the identity. Well, the same thing holds true for matrices. You can take matrices to a power. You can raise it to an exponent. If I take a matrix and raise it to the 0 power, I will get, not a number obviously in this case, but I get a matrix, and it just happens to be the identity matrix. If I take a matrix to the first power, I will just get that matrix back. If I take a matrix to the second power, I square it. It's just the same as multiplying it by itself twice, and so on. So we can apply exponents to matrices just like we do in the real number system, and a lot of the same rules and results apply. All right, so the last thing I want to touch on then is what are called transpose matrices, or the transpose of a matrix. And here a transpose just means taking a matrix and interchanging its rows and columns. So if I have a matrix A, and we'll just do another 2 by 3 here, and I'm going to make this really simple. We'll just call this 1, 2, 3, 4, 5, 6. I want to make sure these numbers are different so you can really see how this turns into its transpose. When we talk about a transpose, what we do is we use a t as an exponent to show that it's the transpose matrix. So again, all we're going to do is all the rows become columns, the columns become rows. So row 1 of A is going to become column 1 of its transpose. So we're going to have, instead of a row 1, 2, 3, we'll have a column 1, 2, 3. And then instead of row 4, 5, 6, we'll have column 4, 5, and 6. Okay. And that is the transpose matrix. We just swap rows for columns, columns for rows. And again, there's some things that happen here mathematically when we do this. So let's go ahead and take a look at an example. By the way, we're going to come back and see the transpose matrix again in the last lesson of this chapter when we do some applications. And we'll actually see how a transpose matrix is used to find a least squares line, a linear regression in mathematics. All right, but here's our last example that we'll finish with this for our lesson. So we've got a matrix. We're going to just use that 1, 2, 3, 4, 5, 6 matrix. And again, so we already wrote the transpose. So 1, 2, 3, 4, 5, 6. And now we're going to multiply these two matrices together. So we're going to take matrix A, 1, 2, 3, 4, 5, 6, and we're going to multiply it by the transpose 1, 2, 3, 4, 5, 6. All right, and when we do that, we get, let's see, we'll have 1, 4, and 9 is 14. And then we'll have 4, 10, and 18 is 32. And then for our second row, we've got 4, 10, and 18 is again 32. And then 16, 25, and 36 is 77. All right, so that is our product of a matrix times its transpose. And what I want you to notice is if we were to, so if this is A times the transpose of A, if I took the transpose of this matrix, so if I take this answer and I take the transpose of it, in other words, the first row becomes the first column, the second row becomes the second column. Notice that they are identical. In other words, I took this matrix, A times its transpose, and I took the transpose of that. I again get the exact same matrix back. So when that happens, we call this matrix symmetric. So we're going to say that A times A transpose is symmetric because the matrix is equal to its transpose. Okay, so A times its transpose is symmetric, meaning that an m by m matrix, and these do have to be square matrices, an m by m matrix is equal to its transpose. So that is always true. That's not just for this example. This is always true. If you take any matrix, any square matrix, you multiply by its transpose, you will always get a symmetric matrix. You'll always get a matrix that is equal to its transpose. Okay? So that is it for this lesson. And again, I will see you in the next one.